All right, welcome back to Taylor-Maclaurin series. In this video, we'll be discussing the third and final type of error or remainder problem that we need to know for infinite series. This is in the formula book. But before we get into it, I just want to distinguish, because I haven't been clear on this, between a Taylor series and a Taylor polynomial. Basically, the series it's an infinite series, whereas a Taylor polynomial is finite. And we've done problems with this before. I just haven't been specific about the language. So the problems where we found, like, find the first three terms of a Taylor series, that we're finding a Taylor polynomial that has three terms. Find the seventh degree Taylor polynomial. It's finite, it's a polynomial. If it's infinite, it's a series, and the formula book distinguishes between the two, right? This top line is a Taylor series, and we see that it's going on forever. The second line is a Taylor, here it comes, approximation with an error term. So we've got a Taylor polynomial, an nth degree Taylor polynomial, and then there's this extra piece that they're labeling as r sub n of x. That's the remainder that we get when we're taking the nth degree polynomial. So it's the first n terms of this infinite series, and then whatever's left over is our remainder. And what is our remainder? There's different forms to write it in. We're going to use what's called the Lagrange form. Don't worry about that name. I mean, like, it'll show up in problems maybe where it'll say use the Lagrange form, or it's the only form. If we're doing error with Taylor, this is the form we're going to use. Anyway, so that r sub n. And most of this formula is really not that bad. It's actually fairly automatic. Let's say we had worked out previously the sixth degree Taylor polynomial. Then I know that the error, r sub 6, is going to be equal to the seventh derivative. Again, we'll talk about C in a second. But it's the seventh derivative. We're going to divide, by 7 factorial, and we're going to multiply by x minus a to the power of 7. And in the problem, we will have been told what that center was, so we don't even need to figure that out. So it's really just C that we need to discuss. What is C? It's just some number that is in between the center of our interval of convergence and x. Now when I say x, we're going to be using our whatever degree Taylor to approximate some value. So in previous video we saw like approximating pi with the first few terms of the arctangent expansion. We also looked at the approximated L.1 of 2. In the video before that, we approximated E. So in each of those, we picked a particular value for x, and we had a center of convergence. So our error can be approximated by choosing a suitable value of C in between a and x. In practice, what we're going to be doing is choosing a value of C that would maximize that error, because we're going to try to be finding an upper bound for the error, like we did in previous error questions. So let's look at a few. Let's start off by finding an expression for the error term of e to the x when we use the second degree Maclaurin polynomial. So second degree Maclaurin polynomial, I grab my formula sheet. It's sitting there right in front of me. Second degree should look like that. That's very easy. Since I've found up to the second degree, which used the second derivative, that means that my error term is going to be calculated by using the third derivative. Evaluated at C, whatever that is. I multiply by x cubed, I divide by 3 factorial. Again, the 3's were all given to me by the fact that this was the second degree polynomial up here. The center of the interval of convergence for e to the x can be shown to be 0. So C needs to be somewhere in between 0 and whatever the x value is that we are approximating. What is the third derivative evaluated at C? Well, our function is e to the x, so the first, second, third, any derivative of e to the x is going to be e to the x. So the third derivative evaluated at c is just e to the power of c. So e to the c times x cubed over 3 factorial, that's my error term. So far so good, I hope. Now let's be a little more concrete. So let's say we approximated e to the 0.75. All right, so that's my x term now. So my error is e to the c times 0.75 cubed over 3 factorial. Now I want to get an upper bound. So I want to choose the value of c that's going to maximize this error. C needs to be somewhere in between 0 and 0.75. Well, e to the x, that is an increasing function, right? We can visualize that very easily. So that means that the largest value for this entire error is going to be if I choose the largest possible value for c. Now, I know technically c can't be equal to 0.75. This is an open interval here. But given that there is no maximum number closer to 0.75, we'll just use that. We'll put 0.75 in, and I can say that the error is for sure going to be less than whatever this is. We grab a calculator, punch it in, that's our error. Now throughout this lesson, let me be clear, it is completely asinine what we're doing. Okay, we are going to be using technology to answer questions using techniques that were designed before technology was invented. We use the technology to get, to take these shortcuts because it's annoying for us to work out things with gigantic decimals, but in principle we could. So our error must be smaller than this. We could check. What is the actual error? Well, it's certainly smaller than what we just calculated for our upper bound. It's almost half of it. Don't put this down as your answer on the test, though. That'll be the wrong answer. You need to get this as your answer. Let's do another one. Continuing to work with e to the x. So now let's try to estimate it with error less than this. So in other words, like how many terms are we going to need? We start off by assuming that e is less than 2.72. Why? Because our ancestors didn't have an e button that they could press on the calculator, so they didn't know as many digits of e as we do now. I'm sure they could have worked out that it was at least less than 2.72. Okay, so we're requiring that the error must be less than that. This notation here from our book is just saying the error of this is our x value and this is our center. So it's a Maclaurin polynomial, so it's centered at 0. You don't feel any need to use this particular notation. It's unnecessary. Anyhow, we require the error to be less than this decimal, though. Okay, we don't know how many terms we're going to use in our approximation, but however many terms we use, we know it's going to be one more than that, what we're going to have to pump into our error term, right? So it'll be x to the n plus 1 over n plus 1 factorial. It's the n plus 1th derivative evaluated at c, but as we just said, regardless of which derivative we're taking of e to the x, it's still e to the x. So our e to the c there is our n plus 1th derivative. And well, this seems like something we can easily do on a calculator. So once again, we're going to use technology to answer a question that's supposed to be done without technology. Marvelous. Before we use our calculator, though, we need to get rid of that c term. Now, we said in the beginning that e, as in e to the power of 1, should be less than 2.72. Our c value is somewhere in between 0, our center of convergence, and 0.4, our x value. Both of those values are going to be less than e. Right? I mean, e to the 0 is 1, e to the 0.4 is whatever, some number, but they're both less than e. So whatever e to the c is, it's definitely less than 2.72, so we can feel free to make this substitution right there, and then it's calculator, graph the thing, find the intersection, and you'll get n has to be greater than or equal to 6. One more problem with e to the x. Some questions ask you to prove that a Maclaurin series, as it says here, prove the Maclaurin series for e to the x is valid for all x. I've also seen it phrased as prove that a function is equal to its Maclaurin expansion. There are two ways to go about answering this type of question. The way that I would probably do it is I would just show that the interval of convergence for this particular function is infinite. And again, we can do that by using the ratio test. We're going to calculate the limit as n approaches infinity of. It's going to be x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. This comes out to be limit absolute value of x over n plus 1. Since n is going to infinity, this denominator is going to infinity as well. So this whole thing is going to go to 0. So that means that the interval is infinite. No matter what x is, this limit's always going to be less than 1. By the way, where am I getting this expression from? Well, I know the Maclaurin expansion for e to the x from the formula book, and I can rewrite that in sigma form. N is going from 0 to infinity, and this is pretty clearly x to the power of n over n factorial. So that's where that's all coming from. So if you can show that the interval of convergence is infinite, then clearly the Maclaurin series is correct for all x. The other way to do this is to show that there is no error. So essentially, like the more terms you take, your error term is diminishing towards 0. And we can do that with limits. So the more terms we add, we just want to show that this limit goes to 0. That's not necessarily the easiest thing to do, though, so we can ignore the e to the c for a moment. We have the limit of x to the power of n plus 1 over n plus 1 factorial. You can show that that's 0 using some fancy limit rules and such. I will just offer a brief heuristic argument for why this is true. Let's just do, rather than x to the power of n plus 1, let's just look at x to the n over n factorial. Same thing, we're just changing n plus 1 to n. This is equal to a whole bunch of x's being multiplied together. How many x's? Well, there are n x's up there. And then this is divided by, it's n factorial, so that's n times n minus 1 times n minus 2, and so on, times 3 times 2 times 1. Okay. How many values are there here? There's n there. So as this grows, if I increase n by 1, then my numerator would grow by an extra factor of x, and my denominator would grow by a factor of n plus 1. And if n grows again, then my numerator would grow again by a factor of x, and my denominator would grow by a factor of n plus 2. So every time that I increase n, my numerator is growing by the same factor, but my denominator is growing by larger factors each time. So at some point, my denominator will begin growing faster than my numerator. So therefore, the limit has to go to 0. Now that's not really as airtight as some of you might prefer it to be, but I think it's easier than any of the solutions that I happen to read for this problem. So in showing that, that justifies that the Maclaurin series is valid because there is no error in the limit as n approaches infinity. Enough about e. Let's just look at one other type of function here. So we're dealing with sine of x. We've got a center of pi over 4. We're going to estimate sine of pi over 5. So I've got my center, and I've got my x value already established. Let's look at a and b first, and then we'll talk about part c. So we can't just use our Maclaurin series because this is centered at pi over 4. So let's just calculate a couple of derivatives out here. evaluate them at our center of pi over 4, and here we've got the coefficients for our Taylor series. No big deal. It's going to look something like this. Marvelous. And now we can use that to estimate the sine of pi over 5 by dropping pi over 5 in for all of the x's. And if we grab a calculator, we can establish that that's approximately that decimal. So now let's show that our approximation is accurate to at least 3 decimal places. Again, that does not mean going to a calculator and actually working out that indeed it is. Yes, we're off by about 0.00001. So great. First 4 decimal places were all 0, but not valid. No points for that. Sorry. Instead, we're going to use the Lagrange form of the error term. Now, we use a 3rd degree Taylor polynomial, which means that our error term is going to involve the 4th derivative of sine. And of course, the derivatives of sine are cyclical. So the next derivative here after negative cosine is going to be sine again. So that's why we see sine of c showing up in our error term. Here we've got x minus a all to the power of 4. But x and a were both told to us in the problem, and we divide by 4 factorial. Now we want to try to maximize what that error might be. Well, I don't actually know off the top of my head the value of sine of any number within that interval. But you know what? I know that the maximum that sine could ever be is 1. So if I want to really maximize this error, let's just throw 1 in for sine of c. If we do that, turns out, look, we still got 4 zeros after the decimal place. So our error is definitely accurate our approximation rather, is accurate to at least 3 decimal places. So we didn't even need to choose a value for c that was in the interval between x and a. We actually went beyond the boundary in this problem because it was easier to find an even higher value that still satisfied the answer to the question correctly. So this c value business, it can be very tricky. As always, what do we just need to do? We need to practice as many different examples as possible, and I've got you covered. If you go to the class website right now, we've got a whole large set of Taylor and Maclaurin and other power series problems. They're called Power Series Practice 1, 2, 3, and 4. These are all problems that I've taken from old BC calculus exams. If you want more problems, you can just Google BC calculus FRQ for free response questions, and then just pick a year. They're all legally released, so you can just choose any year you want, and it's going to be a very high percentage that you're going to find a Taylor question somewhere in there. It's usually problem 6. So here we go. Here's a Maclaurin series. We're finding a bunch of terms, interval of convergence, changing now to a Taylor, and they're using the alternating series error rather than using the Lagrange form in this particular question. That's okay. That's the questions, and then you just look for something that says scoring guidelines, and that'll give you the answers. And incidentally, how they score points in AP Calc, but whatever. The point is there's like no shortage of problems out there for you to find on this particular topic. So go do them. The more you see, the more different perspectives on it you'll get, the better you'll have a more holistic understanding of the topic. And that, my friends, is really the end of section L. As I've promised, I will do one more video on this thing called the binomial series, which does show up in L.3, but as I've said, there's never been an IB question about it, and I don't see those words appearing in the syllabus, so I'm very skeptical that it would ever show up on an exam.